Today I'll be doing a little bit of a detour from my previous video series on explaining machine learning concepts. Instead, this video will be a bit more practical in nature and may be useful if you're first trying to build a machine learning model in a real-life application. That's because today I'll be going over the exact steps to building a neural network machine learning model, with examples of real code. Before I do that, a bit of a disclaimer. Because this is a guide to building a model from start to finish, there will be lingo and concepts that you may not be familiar with, especially if you're new to the field and you've been following my videos to learn about machine learning. That's okay. This is only my fourth video, so naturally I have not yet explained a lot of things I'm going to talk about today. So why am I making this video now? Well, pretty soon we're going to start to dive straight into what's called a neural network, which is in my opinion the heart of machine learning and deep learning. They can be pretty confusing. I think it's helpful to understand the high-level structure and flow of how these models are set up, especially if you're planning on building and working with models yourself. And while we're at understanding things in a high level, what better time to go over the entire framework of a typical data science machine learning model building than now? So without a further ado, like and subscribe if you haven't already, and let's get started. First step is always the one that is so underestimated, and that is to define your problem and what you want to do. It may sound obvious, but you'll be surprised at how many models get started without a clear goal, and that can lead to some unhappy results. So ask yourself, what problem do you want to solve? There's a lot of things that machine learning can do, but if you're a beginner looking for something simple, this question will probably lead to an answer that starts with either I want to predict something or I want to classify something. And the next question you want to ask is, do you need an ML model to answer this question? Of course, if your goal is to just practice and use a model to do something fun, then go for it. But in the real world, if you're working as a data scientist or an ML engineer, someone will inevitably ask you if you can build a model to do something that really doesn't need a model. If you're living in 2025, which is when this video is made, AI is taking the world by the storm, and your boss might want you to build a complex model leveraging state-of-the-art models to make a prediction that, well, could be done with a simple linear regression. If you've set your mind on building an ML model, the next step is to find or gather the data. And unless you're working for an organization that can organically create data, getting your own data might be tough. And creating or collecting your own data is an entire field of study on its own. So let's stick with finding data online. You can do this with various sources. Some popular ones for machine learning projects include Kaggle, UCI Machine Learning Repository, Hugging Face, Data.gov or US Census for government data, and NIH or WHO for health-related data. And really just about any renowned organization that collects and does research also publish their own data that you might be able to get for free. If not, popular packages for machine learning like sklearn or Keras have some toy datasets that you can use as well. Old school Google searching can also get you there. You can specifically go to Google Dataset Search, which will be tailored to data sources that you can trust. My recommendation for beginners would be to use Kaggle. You can come here and search for any keywords, select the data, and then just download the data. For example, we're going to search for a dataset on housing prices. Go into any of them. This one is actually a part of a competition, so you may have to find them in the competitions tab, but the interface is really the same. You can preview the data, and there is usually a usability score that I'm not seeing for this one in particular, but it'll basically tell you how well organized the dataset is, which can be a useful metric for you to consider when picking the dataset. You can also see what other people have done with the dataset, so you can get some ideas. Data setup. Now we're going to get to the coding part, so open up your favorite IDE. I use VS Code, but it doesn't really matter what you use. We're going to code in Python, and you'll need to import the packages that you'll use. Don't worry, you're not expected to know all the packages before you start to write the code, but you will need to choose which deep learning library to use. There's two in particular you should know. Both TensorFlow and PyTorch can do the same thing, but require a bit of differences in the structure and the syntax. My personal opinion is that PyTorch is slightly easier to use and requires less coding, but TensorFlow feels more structured and makes it a bit easier to understand the exact steps of what's going on. We're going to stick with TensorFlow today. Others you'll probably use are NumPy and Pandas as always, and scikit-learn has a lot of statistical and machine learning packages you can use. You'll probably also want to have some kind of visualization, and your standard Matplotlib and Seaborn can take care of these. The dataset we downloaded from Kaggle came as the form of 2 CSV files and 1 TXT file. You can ignore the sample submission.csv. This dataset already came in split between train and test, which means it'll save you some lines of code that you'll otherwise have to write. Although this already came split 50-50, I'll still show you an example of data splitting later in this video. The data description file is where you can see the definitions, labels, and other information about the data. This came in pretty well labeled, but other datasets might not offer you this level of detail. Important to note that while there are 81 columns in the train, there are only 80 in the test. That's because this dataset is actually from a competition, like I mentioned before, where we have to predict the 81st column, the sale price of the home. So while the train dataset needs that column for the model to learn, the test data didn't include this column. So load both your train and test datasets. I used Pandas read CSV method to specify the path where the data lives in and load the data. If you have data coming in other formats, Pandas will likely have a data reading method like read TXT, read JSON, and so forth. Or if you're using one of the toy datasets, the library will usually have a load data command that you'll have to import. The next, and arguably the most important step, is data cleaning. Important because the model will only be as good as the data that it is using to learn. In other words, having garbage data means having garbage model. The most important thing for building a machine learning model, of course, is to make sure that all of the fields that are being used in the model are clean. As you might imagine, every dataset is different and has varying levels of cleanliness. With every dataset, you'll have to do different kinds of data cleaning. But for simplicity's sake, here's a checklist of the most common things that you should be looking for. Missing values. You'll encounter data with missing values. In many data analytics types of work, missing information usually doesn't signal anything concerning, but in certain situations you will need to explicitly address them. In neural networks in particular, missing values will actually prevent the model from running, so you will need to do something with them. Easy solution is to remove the data that contains missing values, but you may not want to do this for obvious reasons. You can also choose to impute them with a value, meaning you replace missing information with a substitute. If the column is numeric, something like mean or median imputation is common, but you might also just impute them with a certain number that you know indicates missing information. If you decide to impute missing values, there are some helpful packages you can use to make the imputing process really simple. Also, you'll sometimes encounter missing information directly stated, like these. These aren't technically missing values, so they're actually fine, but you might want to change how these are expressed. More on how to address these a bit later. Data types. You want to make sure that the data that you're using is in the correct format. Oftentimes you'll see a column that seems to be just numbers, but then the actual data type is coded as string. Turns out, while these are numbers, missing information got coded as string NA, or there are certain values that are a combination of words and numbers, like this one, which made the column into a string of numbers or an object type. There are methods and techniques that are only doable with certain data types only, so it's important to check for these always. For modeling, whether or not columns are numeric, ordinal, or categorical is also a big deal. We'll talk more about these later as well. Outliers. This one is a bit subjective because it's unclear whether including outliers in the data helps or harms the model. The answer is it depends, so you have to be considerate with it. If you have a good reason to remove outliers, then go ahead. If not, you may consider keeping them, and perhaps the model will figure out what to do with them. But at the very least, check whether or not your data has outliers. Duplicates. For whatever reason, your data might include 2 or more rows that appear to be the same. In this case, you will have to decide whether or not you should remove duplicate rows. I would say just be careful to actually verify something is a duplicate, because you might make the mistake of accidentally not looking at a particular column that makes these duplicates not duplicates. But if you're sure that there are duplicates in the data and they don't provide useful information, then go ahead and remove them. Pandas has a method drop duplicates that you can use to simply remove them. There's a lot of data cleaning things you can do, but as you can see, data cleaning and the resulting transformations really vary from data to data. The important thing to have in mind is to just make sure that the data is in a very solid, clean state before you try to do any analyses or modeling. In our example data, let's take a look at all of our columns with the info method. Right away, we can see that there are some columns that have a lot of missing data. This code prints out the columns with the most missing data. After looking at some of these columns, I think I'm okay with removing columns that have too many missing values. So that's what I do here. I also remove the ID column as it's not really needed. Still, I have other columns with missing data. For those, I decided that I want to impute these with the constant -1. I first check if -1 or any negative value exists in the data, as I obviously don't want to put in a value that might interfere with the data. As for the actual imputation code, I'll do this a little bit later when I get to the feature engineering portion. But instead, before I make any changes in the data columns that I have left, I want to do some exploratory data analysis, or EDA. EDA doesn't have a definitive form. As its name suggests, it's quite exploratory in nature. And quite literally, you explore the data you have in front of you. As a matter of fact, the data cleaning you did just now is part of EDA. You wouldn't have known that there were missing data or duplicates or outliers hadn't you done an analysis into your data. As such, EDA and data cleaning often go hand in hand, and you'll most likely iterate between them in a loop. More EDA you do, the more things you'll find that needs to be cleaned or transformed. But you also have the analytical piece of EDA, and this will be even more freeform. Depending on the project's goal and hypotheses you might have, you may want to do some non-modeling analyses before you build a model. In our case, we're trying to predict housing prices, so we might explore what factors correlate most with sale price, like this example. A simple linear regression might be done with one of the variables to just see a more detailed relationship. You might wonder how the age of the house affects its prices by looking at that relationship, and so forth. As I mentioned, more EDA should lead to a better understanding of the data. You might notice that in this particular year, prices were very high. This might be due to some abnormal event, or simply a low sample size of the data in this year. So you may choose to look more into this to see if this data needs to be further refined. See what I mean by this loop? Feature engineering is a type of data transformation process that works in a similar way to data cleaning. As a matter of fact, the distinction between feature engineering and a typical data transformation from a data cleaning procedure isn't black and white. The way I'd like to differentiate feature engineering is to think about whether the data transformation I'm doing is related to the model I'm interested in running. To go straight into our example, we know that the neural network does not allow for missing data, so we should impute missing values with something. We decided to impute with the constant -1. For that, let's first identify the columns that we have that are missing values. But it's important to understand that imputing with a constant can have different impact depending on the variable. For example, a column of numeric values, such as the lot frontage area, the year when something was built, and the mathematical area are our numeric columns. For these, replacing missing values with a numeric value obviously skews the data. That's why I also decided to create new columns that simply indicate whether a value is missing or not. This little for loop creates new columns that act as a flag, so our model can distinguish where there is a missing value. For categorical and ordinal columns, the -1 isn't as impactful, but I decided to create new columns for these as well. You'll notice I impute them with the word missing for categorical, but I'll be changing them later, so don't pay too much attention to them now. Then I define my ordinal and categorical variables. I do this because I need to treat them differently. Ordinal variables benefit from the fact that their numerical representation has an intrinsic value, so the model should use them. But if you saw the data description, the ordinal variables, such as this one, have values that our model wouldn't be able to understand. After all, we know that excellent is better than good, but how is the model supposed to know that the characters EX is better than GD? So we have to recode these into numeric values. And that's what I'm doing here. And I also changed where I previously recoded missing values as missing into -1 as well. Categorical variables, on the other hand, we have to make the model understand that there is no clear intrinsic order to whether the column neighborhood has values Bloomington Heights or Bluestem. Making Bloomington Heights 1 and Bluestem 2 might incorrectly make the model think that Bluestem is better than Bloomington Heights. So I'm doing what's called a one-hot encoding, which is available for easy use through the sklearn package. These just create indicator columns for each of the available value labels. So the neighborhood column will turn into several columns for each distinct neighborhood, each being a binary indicator of whether or not the neighborhood was selected or unselected. You can see here that all this feature engineering has stretched our columns into many more columns. I see here actually that our train and test data sets ended up having different number of columns. This is due to the test data set somehow having certain columns where one or few of the value labels didn't exist in the data. So the one-hot encoder didn't create a column for that specific label. I don't really like this, so in this cell I'm removing columns, except sale price, that exist in only one of the two datasets. Note that this may not be the best practice always, but I'm doing it anyways. And finally, at the end of feature engineering for a neural network, all columns should be of numeric value, so it's a good idea to check that before moving on to the next step. The next thing you have to do is to split your data into train and test. As I briefly explained in a previous video, train is the dataset you use to build your model, and test is where you evaluate with new unseen data. Typically, I like to do all of the data cleaning and transformations before splitting, but this dataset already came split, so I had to do all of the data transformations to both datasets. Another thing that I don't really like is the fact that the data was split 50-50. In a machine learning assignment, I like to split closer to 70-30 or 80-20, but it came 50-50. If possible, I might randomly select rows from the test and move them into train, but you saw that the train dataset actually had the sale price column removed already, so I won't be able to use that anyways. So I will keep it as 50-50. However, one concept that you can use is to have a validation set. Validation set is a small subset of your trained datasets that you use to run your trained model, see how it performs, and then further tune your model. So it's like a mini test set that you can use to fix your model before the actual evaluation with the test set. Now comes time for the actual model building. And as I said in the beginning of the video, even if you might not understand all of the specific terminologies and techniques, just bear with me, and I'll explain these concepts further in the upcoming videos. The main thing I want you to grasp is the overall flow of how to build a neural network model. You don't have to do this, but I like to put my neural network model building into a single function, as you might iteratively run this function multiple times, experimenting with different parameters. First thing that happens is really optional, but including this clear session code frees up memory and resets the internal state, which helps prevent any potential conflicts. The next part is the actual design of the neural network. The one I have built is a very simple one that only includes the basics, and these are built with the TensorFlow library. Without going too deep into what is a neural network, it's a type of model that has an input, expands them into a large set of hidden layers consisting of connected neurons that each carry a weight. Through these layers, the connected weights learn patterns that allow them to narrow down and output a final weight that essentially predicts the output. And the learning happens over numerous batches and epochs through a process called backpropagation. With TensorFlow, you'll want to start defining the model with a Keras sequential, which creates the model which is going to be a sequence of layers. Each fully connected dense layer are going to be defined by specifying how large you want the layer to be. It's common to decrease the layer size in the network so that the neural network can eventually condense complex relationships into more focused patterns. It then has to output something that would go into the input in the next layer, and this is done with the activation function, which is in this case what is called ReLU. Between each dense layer, we can put in a dropout layer which drops a fraction of the neurons in order to prevent overfitting. At the final layer, we need to output a single value, so we want to reduce the unit size into 1. The activation you want to use here is linear, which in this case just means that we don't want to do any activations. After the model building, you'll combine the model by specifying the loss function you want to use and the optimizer you want to use. I explained a little bit about this on my video on gradient descent, so check that out. But basically, the model learns by minimizing loss. And so you have to specify how you will define that loss, which in our case is the mean squared error. You also want to define how the model will learn by adjusting its parameters, and that is done with your choice of optimizer. And you can choose to also output a series of metrics. For our case, I think looking at the mean absolute error and its percentage error would be helpful than interpreting the squared value, so I included those. The next bit of code is to run the model you have just defined and to fit the model against your training. So you can see how the model learns with your training data, and it shows what it looks like when running against the validation data. Running this code will output the loss and the metrics you specified, and you can see how it changes for each epoch. Hopefully you'll be able to visualize that over the epochs, the loss decreases, meaning that your model is learning. The mean absolute error, MAE, and its percentage, MAPE, lets us easily evaluate if the model is doing a good job of learning to predict the sale price. By the time we're finished with training, we're able to get within a $16,000 error range of the correct price, which in my opinion is pretty good considering prices can easily cost in the hundreds, thousands, and even millions of dollars. But if you want to improve your model further, you can mess around with the design of your neural network and your parameters to try to see if you can make the model better. Or even go back to the data cleaning or feature engineering sections to see if you can improve the model simply by changing the way you transform and set up your data. Once you're satisfied with the training, you can use a simple one-line code to actually output the model's predictions using the test dataset. So there you have it. This is a very simple neural network model that we just built from raw data. By no means is this the perfect model, but this should have let you see the high-level flow of how a model building works in general. And in the larger picture, this entire flow that we went through in this video is pretty much a simplified version of a typical data scientist workflow if they are the type of a data scientist that builds models for analyses. Now you might wonder, so how do I actually use the model that I built to do cool things in real life? There's actually a whole beast of using models in production, which includes things like deploying a model, architecting the systems, building an application, hosting it in the cloud, and etc. For a traditional machine learning data scientist, though, being able to build and evaluate models will get you started.